In this short video, we will see how we can compute this challenging limit in two different ways. First, without using the Hospital rule, and in the second time we will use the Hospital rule. This limit is challenging indeed, because here if we take x equal 2, we get 0 here and 0, and we have 0 over 0. In the classical case, when we have a polynomial here and a polynomial here, we can factor by x minus 2 and cancel. But here, as you see, this expression is not a polynomial, and also this expression is not homogeneous. So we need to find a way to factor this quantity and this quantity. So the first way to handle this situation without using the Hospital rule is to transform this quantity on a quotient of two polynomials. So we will see that this quantity is indeed a rational fraction, and also this quantity is a rational fraction, and it is, in my opinion, the challenge, the trick we will use in this computation. So we will see how to do this, and it's based on a formula, an algebraic identity, the identity a power n minus b power n equal e minus b sum from k equal to 0 to n minus 1 ak b n minus 1 minus k. And by using this formula, we can write this quantity as a rational fraction, and we will see that the coefficient x minus 2 will appear, and then it will cancel, and we can compute. So the interesting part is the technique how to transform expression like this in a rational fraction. We will use this formula for n equal to 6, and we have this formula. So you have the hint, and you can try to compute this limit without seeing the solution, and go to the solution after. So let's start. So we will start by transforming the numerator and the denominator as a rational fraction. Okay, so the numerator is the difference between two quantities, ax minus bx, where ax is equal x minus 1 power 1 over 6, and bx 3 minus x 1 over 2. And we will use our algebraic identity to compute ax power 6 minus bx power 6. And if you compute ax power 6 minus bx power 6, here you get 6 over 6, so you get x minus 1, and here 3 minus x power 3. And the question is why we have chosen 6 here. and 6 is indeed the least common multiplicator of 2 and 6. 2 and 6. So if you have two other quantities of 1 over p and 1 over q, you can choose the least common multiplicator of p and q. So it's the rule for tackling the general case. Now, so we get that this polynomial ax power 6 minus bx power 6, which is equal to this, as we can expand and get this expression is x power 3 minus 9 x2 plus 28x minus 28. So we have this. Now we will use, we can see first that a2 is equal 1 here and b2 is equal 1 2, and so this polynomial p2 equal to 0. So this polynomial have a root 2, so it can be divided by x minus 2. So if you do so, you get that this polynomial is equal x minus 2 x power 2 minus 7x plus 14. Now we have expanded this expression and we have now x minus 2 as a factor, and since we will compute the limit at 2, now it's interesting to have this equation. Now we will use our algebraic identity. A power 6 minus b power 6 is equal to. So if we plug ax and bx here, we will get that this polynomial ax power 6 is equal ax minus b factor of polynomial. So we get now that this quantity is equal ax minus bx qx with q1x, which is a polynomial. So now we have down with the numerator, now we have that the numerator is the quotient of these two polynomials. Okay, now so we can replace and get this first expression. So it is the trick we use to transform this quantity on rational fraction. Where q1x is this quantity, we don't need to compute it explicitly, because what we need is just to compute q1 2, because when we take the limit we will take q1 2, and q1 2, because a2 is equal 1 and b2 equal 1, q1 2 is equal to 6. With this information we don't need to have explicitly this polynomial. Now we will do the same for the denominator, donc dx equal x minus 1 power 1 over 2 minus x minus 1 power 1 over 3, and we write it as the difference between two expressions, and we use our, so here we have 1 over 2, and here we have 1 over 3, and we will take the least common multiplicator of 2 and 3, which is also equal to 6, and we will compute cx power 6 minus dx power 6, and we get this expression, and here we can take x minus 1 power 2 as a factor, and we get x minus 2, and it's what we are looking for. And now by using our algebraic identity, we get that this polynomial is equal the denominator and q do polynomial x, and now we have that our denominator is equal to this quantity where q to the x is also a polynomial, and we can compute q to 2, and we get this quantity. So now we have almost done, because now our expression is the quotient of the numerator and the denominator, and we get that this quotient is a rational fraction, and now we can simplify by x minus 2. It's the way to resolve the indetermination, and finally we get this expression. Now we can plug x equal 2 in this quantity and get something which not an indeterminate form, and we will get our limit. So now with this we have our limit. We replace here, we will have 4 plus 14 minus minus 14, and we get our limit is equal to 4, and we have done. Okay, this is the tricky thing, but it's interesting that we have shown that how to transform expression like that on a rational fraction. Now we can use the Hospital rules to see the power of this rule. So we have the numerator equal this. We compute its derivative. Here we have plus because we have minus here, so we get this the derivative of the numerator. We do the same for the denominator, and we get its derivative, and now we can use the Hospital's rule to get that the limit of nx over dx is the limit of the derivative of n over the derivative of xf, and if we replace x by 2 we get the limit. Okay, so thank you, and now you can try yourself to compute this limit by using the technique we have used in this video. And to support the channel, please like, subscribe and share, and thank you.